Hey, welcome back to ECE 3D2. Today we're going to move on to SysTick timer. We're going to talk about how the SysTick timer works. We're going to look at how we can apply it for different embedded system processes, and then we're going to take a look at some of the stuff you'll have to do for the lab next lesson. So we're going to specifically look at theory of the SysTick timer, and then how we could use a timer like that to create a pulse width modulation signal. So the SysTick timer, it performs timer and counter operations in all ARM processors. So it's portable. If you develop this C code for one system, any other ARM system would work as well. And there's two main reasons we use it. The first one is to create time delays. So very similar to the time delays we've already done before, but this is a bit different in that we have a little bit of control on what's going on during the time delays versus when we were using the previous delays, we just were blocking and going into a area that we weren't allowed to, do any other processing. So using the clock delay that we did before prohibits us from doing any other processing while we are delaying. Whereas the SysTick, if we do it correctly, we can process while the delay is occurring. And the other is to generate periodic interrupts. So this Module 9 is going to focus here with the time delays, and then subsequent modules we're going to look at how to generate periodic interrupts. And if you're confused what an interrupt is, so say I have code that's being processed, I have my lines of code, they're going through and we're moving down through this. The way the timer, once that timer is up, it creates an interrupt. And what's going to happen is wherever we are in the code, it's going to stop. It's going to jump to a new portion of code, and it's going to run that until it completes. And then once it's complete, it's going to go and come back to where it left off, and then finish that code until the next interrupt occurs. So say we're moving down, the timer is complete again. We stop this, what we're doing, and then we move back up here for another interrupt. And so that's what a periodic interrupt means. It means periodically we're going to stop what we're doing and do something else. And it's all based off that time. So let's talk about how SysTick works. So it's very basic. SysTick is a very basic timer. You basically have a 24-bit counter that counts down. At the rate of the bus clock. Okay, so that's as easy as it sounds. So we start at a number and we count down at the rate at which the clock is running. And so if you looked at any of the C code we've done in the past, there's this line of code that helps us create this 48 megahertz clock. So we typically are running at 48 megahertz. All right, so if it's at 48 megahertz, that's 1 over 48 e to the 6, which is about, means that the tick of the clock, so, going through and decrementing, each tick is going to decrement at 20.83 nanoseconds. So every nanosecond, so say my clock's starting at 4, 3, 2, 1, 0. It's going to take 20.83 nanoseconds, 20.83, 20.83, 20.83. So this timer, which would count down from 4 to 0, would take 4 times 20.83 nanoseconds. All right, so the way that this is going to work is this counter is we're going to set the 24-bit load value. So software, we're going to do that in software, and we'll see an example of this. So in this example we just said, load was equal to 4. Okay, so that's all that's doing, and then it's going to have a counter, which is called value, goes from n to 0. So our counter in this example, where load equals 4, val would equal 4, 3, 2, 1, 0, 4, 3, 2, 1, 0, so on and so forth, and that goes on forever. This is called a module n+1 counter. So it gives us this ability to loop back, where each time we're going to decrement, and then we're going to modulate, use the modulus counter so that we can then get back to our original value in. So this stuff not as important. What you just really need to understand is load. Put this in gold for important. Load is where we start, so that's our n value. Val is our counter. And all we're doing is starting at n, and we go down to 0. Start at n, go back to 0. N, 0, n, 0. All right, so let's look at what that looks like in the actual registers. So we have these 3 different registers. So this is very similar to port 1 select 0. So somewhere in memory, this select 0 register lives, right? So we have select 0. We have the port 1 select 0. And we saw this in the data sheet, and then that is 8 bits wide, 1 for each of the pins, so on and so forth. All right, this is different in that this is a 32-bit register, and it is part of the SysTick, and the register is called control, load, and value. So again, key things to remember: load is that end value that gets reloaded, or that gets set as the initialization value, and then value is the current value as we decrement. So n might be again 4, and then the first time the val is going to point to 4, then val is going to be 3, 2, then val is 1, then val is 0, and it repeats. All right, so this is our clock source. So that's going to be just set to our bus clock. There's an enable pin, so that's bit 0. So if I wanted to enable our counter, I would go SysTick control, and I want to turn on bit 0. So I'm not doing anything else but turning on bit 0. So I'm going to set it. So I'm going to OR it. With 0x01. That enables it. Easy peasy. What about this count flag? So basically, that's going to be more important for our interrupts. And what's going to happen is every time we get to 0, so let's talk about the count flag. It says count. When val equals 0, count equals 1, else count equals 0. So that's just letting us know that we've gotten to the point where we've completed counting down. So if we go down here, an example, say we wanted to wait an amount of time. And we create this wait function here. And so what's going to happen is that it's going to, we're going to start SysTick load equals n-1, because remember it's an n+1 counter, so we're just going to, there's always 0, so we just do an n-1 to get to that. So say I wanted to wait 30, I do an n-1 because of that 0 count. Okay, and so that goes into our load register. So that's our reload value. So say again, I wanted to wait and this is at 48 megahertz, so whatever value goes into n, so that's going to be our wait, n-1 is going to be our load value. We're going to go down to 0 eventually, so val setting that equal to 0 just clears it so that we can then reinitialize. And so while this count value, so this is what we're doing here, we're selecting the bit, that bit 16, so count is bit 16. While that is 0, we're just going to wait and do nothing. And then once it is at 1, so once it turns to a 1, so once the timer goes to 0, then we're going to stop waiting and we're going to exit that loop. So note that this this loop here is pretty much doing the same thing that our delay is doing. And so this requires all of the processors attention, because we're sitting here in this loop doing nothing while we're counting down. And we're going to count down to a certain value. Once we get to 0, count's going to turn to 1. Once count is 1, then this is going to return a 1, and it's not going to be equal anymore, and we're going to exit. So we can see that in this loop here. So we load n-1, we clear the count flag, we read the count flag, which is what we're doing right here. In the SysTick control, we're getting that 16th bit, which is count. We're selecting it using the AND with a 1. And then we're going to check, is that equal to 0? Have we gotten down to finish our counter? No, it hasn't. Oh, sorry, does that equal? Yeah, so yeah, if it equals 0, then we continue going. If count equals 0, we continue going until our val equals 0. So once val, again, once the count flag, when val equals 0, count goes to 1. Otherwise, count is 0. And so if count is 1, then we return from our function. And we've now created a general 48 megahertz. So this can go up to 349 milliseconds wait time. So if we wanted to be a little bit more specific, say I wanted to create a 10 millisecond wait, right? So we can call our SysTick wait and wait 480,000 cycles, because if we're working at 48 megahertz and I take 480,000 divided by 4e to the 6, I get 10 milliseconds. Okay, so that's all that's happening here. In the code, we're going to, in the lab, you're going to have to create a 1 microsecond timer, and you can see that to do that, we're going to have to wait a certain amount of cycles right here, 48 cycles. So we're going to be able to load, instead of n-1, maybe you would load, so our delay here comes in, and we are going to delay 48 times that delay, right? And then we're going to -1. So that's going to be what we would potentially put into our load value. And that's going to allow us to count, because every time we're going to count, it's going to take 20.83 nanoseconds. And so if we counted 48 times, that would be 1 microsecond. And that's going to, and then our delay comes in to say, hey, I want to make 10 microseconds. So I say 10 times 48, and that gives me that 10 microseconds. All right, that's it for the theory. So we're going to stop this video and start a new one to get into some of the actual how do we use it.